Hello everyone, my name is Otto Randolph, and I'm here to talk to you about automation of an off-grid vertical farming system to optimize power consumption. So, first off, what is vertical farming? Well, it's a broad name for a lot of indoor farming techniques. You may have heard of hydroponics because those are the most common of these techniques, but there are many techniques, some of which are aeroponics, where you grow plants in air and then you mist the roots, or there's also aquaponics. And aquaponics work by having a fish tank with fish that produce fertilizer, and this fertilized water is then sent to the plants, which purify the water, and then this purified water is sent back to the fish tanks. And the reason why all of these vertical farming techniques are being actively researched is that they are much more efficient than traditional farming. If you think of a traditional farm, you're growing food in a flat plot of ground, and you are only growing food for a couple months out of the year. A vertical farm can be grown in 3D because you can stack these systems on top of each other, and because it's an indoor farming technique, you can grow plants all year round. Furthermore, you can vastly reduce the amount of water and fertilizer used in these farms. Traditional farming uses over half of the world's fresh water supply. Vertical farms could reduce this by up to 90%. And then once the water has been spent, you can be selective in what you do with this wastewater, and you can prevent it from contaminating rivers and reservoirs. But while these facts are very impressive, vertical farms do have several drawbacks. In addition to being very expensive to build these facilities, they are very energy intensive, and these energy demands negate a lot of the green positives. But if you combine a vertical farm with a renewable power source, that could solve a lot of these problems. Furthermore, if you do it right, you can actually be much more efficient with the power that's generated from the renewable energy source because of some of the unique characteristics of vertical farms. The first one is that you can be flexible with your energy scheduling. What that means is that if your renewable energy source produces its peak amount of power at a specific time of day, you can schedule your vertical farm to use as much of that peak amount of power as you can, because plants don't have to get light and water at a fixed time of the day. They can have their schedules shifted to wherever is most convenient for the power source. Furthermore, we can also go and vary the demand of the vertical farm based on the available energy supply. If you think of plants in the field, they do not get 8 hours of light a day from the sun every single day. Some days are very bright and sunny, and so they can get enough energy for photosynthesis longer. Other days are dark and rainy, and so they don't grow very much. And so if you have a PV farm that's not producing much one day, well, you can just turn off some of the lights inside of the vertical farm. But if it's a very sunny day, well, you can turn on more lights inside of the vertical farm. Now, some of the requirements for our system that we wanted to create were that we wanted to be fully renewable energy powered, and we wanted to be able to really use every single watt of power that was generated. And to do that best, we decided that we needed to create an off-grid system so we could fully tune our system to match the energy produced during a given day. Furthermore, our earlier results showed that a total power failure was the quickest way to kill the plants inside of our system. And we found that the best way to avert a complete power failure was by automating the system. With these two things in mind, we focused a lot of our prior work on automation and off-grid systems in hopes that we would find a fully off-grid and automated system, but there were none. For automation, most of the research focused on automating individual parts of the system, mainly the watering and fertilizing schedules, and that was found in some large-scale applications where you'd automate one of these, or in some small-scale operations, such as in a laboratory environment, where you try to automate a couple of systems. And then finally, there were a few patents for automated watering and fertilizing systems. Now, for off-grid systems, some researchers had focused on providing ways to monitor remote fields that farmers might have so that the farmer doesn't physically have to go there and look at the field, and the data that the farmer needs can be sent via live feed to him. Others focused on creating microgrids of greenhouses, and so each greenhouse would have its own energy source and a battery pack to store some of that excess energy, and they could share energy between the greenhouses. But the problem with their research is that they still relied on a grid connection for emergency power needs. And then finally, there was one aquaponics system that we found that had a fully off-grid power supply, but the uses of electricity in that system were limited. The lights for all the plants just came from the sun, and the energy that it did use was only used to transport water from the fish tanks to the plants and back again. Now, for our system that we created, we broke it down to 4 main subsystems: lights, air conditioning, fans, and pumps, and we weighted them differently based on their importance to the plants and the amount of energy that they used. For us, the first thing that we turn off if there's a power shortfall was lights, and that's because lights used 85% of the power generated on a typical sunny day, and they were the least critical for short-term plant health. The lights could be turned off for several days or run at a reduced capacity and the plants would be fine. The next thing that we'd turn off would be air conditioning, because without the lights you don't have as much heat being generated inside the system, and the fans inside the system can keep the temperature to roughly the same temperature inside as outside. But the air conditioning is important to the plants to keep them at the optimal temperature range. But it's just because it uses so much power that's why we turn it off next. Now finally, fans and pumps use a negligible amount of power each day, so they are the last things we turn off. And pumps especially will be the very last thing that we want to turn off, because the plants would very quickly die without water. And this is especially true on hot summer days, because the plants would very quickly wilt and then die if they didn't have water access. Now, for our philosophy with how we wanted to use the power, we really wanted to match energy generation, which is the blue line, with energy consumption, which is the blue bar. And the reason we wanted to do that was because we have a limited battery pack. The battery pack is only 10 kilowatt hours of usable power, and the system on a typical summer day uses 80 kilowatt hours of power. So we can't have too much disparity between energy generation and energy consumption. Furthermore, The reason why we made the battery pack so small is because batteries are very expensive and they have a short lifespan, and they are also harmful for the environment once they are bad. Now, the other limit that we did have is we had a 7 kilowatt hour power inverter. So once we got to, if the sun produced more than 7 kilowatt hours of usable power, then any excess energy would need to be stored in the battery pack or wasted. So with that being said, the first thing we wanted to do was simulate the entire system and compare a fully automated system to our initial system, which worked off of a series of timers, and then we wanted to physically implement the automation onto our time system and see what improvements we got. So for simulation, we simulated our system in Arena, and we created 5 sections for our Arena model. The first section that I want to point out is temperature, and all that does is take in historic temperature data and import that into the simulation so it can be used by the climate control system. For the rest of the system, it focuses on watching where the power comes in and leaves the system. So energy comes in, and that's determined by historic weather data, and the first thing it goes to is a decision node to determine whether the battery is full or not. If the battery is full, then the energy is wasted. But if it's not full, then the energy is stored in the battery until it's needed. Next, we have the pumps, and if there's any energy available in the system, it will first go to the pumps, because, as we mentioned earlier, they are the most critical subsystem. If there's a power surplus and we have enough energy stored in our reserves, then the next thing that we turn on is the climate control system. And based on the temperature, we can go for the minimalistic route of only running the fans, or if the temperature is very hot outside, then we can run the full air conditioning system, which uses a large amount of power. Finally, if we have enough power in the reserve of the battery pack and we still have power coming in, we will turn on lights up to the inverter limits. Now, running the system and having it act as a fully automated system showed that in summer months we could run 7 to 8 racks of plants, and that's because of the very long and cloudless days that we have in summer. But in other months, like in February and December with the short and rainy days, we found that we could only run 2 racks of plants for 8 hours per day. But for every month of data that we ran, we found that the system never lost power, no matter what happened. Now, when we then went and tried to simulate a partially automated system that ran off of timers, we found that at best it would never lose power, but at worst it would only have 86% power stability. Now, the number of racks that we ran in each of these months was based off of the results of the previous section, but one thing I want to point out is that this is a best case scenario for the partially automated system, because we assume that power is immediately restored after a power outage and that the schedules of the timers are not affected. Now, for physical implementation, the first thing we needed to do was create a control algorithm, and the best process that we found was to create an iterative process. And the first part of this iterative process is we want to determine the number of units to run. So we start off and we look to see how much energy is flowing in and out of the battery pack, as well as the number of units that we ran last time. If we have excess power, then we turn on another unit. If we do not, then we turn off a unit. Then this suggestion is then run to the next part of this algorithm where we look at the state of charge of the battery, and from there we determine if we want to run more than the suggested number of units to run or less than the suggested number of units to run. Once we know how many units we want to run, then we have to determine which units we turn on. So to start this process, we turn off all of the running devices, and then we look at the number of units we want to turn on. If that is greater than 0, we turn on one of the available devices and subtract 1 for that number, and we keep doing that until the number of units we want to turn on is either equal to 0 or we have no more devices to turn on. At which point, in either case, we run the system for t seconds and begin the process over again. For our system itself, we relied on a network of Raspberry Pis, and we did this because the Raspberry Pis we saw were used by many other researchers, and there's a large support database for us to go to. Furthermore, a lot of the available equipment was plug and play, and we could easily integrate it with the existing hardware. Now, we went with a central hub Pi setup where the central Pi collects the data and controls the servant Pis, and we created a Modbus connection to the solar panel computers. And here's an overview of how it looks. So raw data is sent from the solar panel system, and it's interpreted by the Modbus and sent to the hub Pi. Furthermore, temperature data from inside the shipping container with the plants is sent to the hub Pi, and all of this is inputted into the control algorithm. The control algorithm makes its decisions and sends its decisions via the Wi-Fi router to the servant Pis, which turn on or off the outlet relays to the lights and air conditioning systems. Now, the results were partial automation, where that over a 7-month period when we had the system fully running, it would routinely lose power. The outages ranged from seconds to hours, and they would continue and oftentimes get worse until the timers in the system were physically reset. Furthermore, especially in times when we were generating some power but not enough to fully operate the system, we would actually damage the components by having the system turn on and off repeatedly in a very short amount of time. Now, when we implemented the full automation, we ran the system for 2 months, and over those 2 months, we only had 2 power outages. At most, they lasted 5 minutes, but the time that they lasted was negligible, and they only occurred after days of cloudy, rainy weather, which in the other system, that would have happened on the first day of cloudy or rainy weather, and it would have just gotten worse. So, in summary, farming needs to become more efficient, and off-grid vertical farms could be the answer. For the fully automated system, the simulation never lost power, and the physical information only lost power for minutes. So, in conclusion, automation is the key to power stability. Thank you.